Everybody's Tyler here at the World Championships, checking in with world-class 1678 Citrus Circus, ranked number 3 on the FRC Top 25. Speak more about this fantastic robot, by the way, I have Zach, Helena, and Apoorv. And this machine, holy cow, let's go through the complete package here. Of course, we'll follow that cargo journey, an incredible cargo ejector that they've had some great strategy with throughout this whole time. Amazing climber, some great software. Let's talk more about this robot coming up here on Behind the Bumpers.
Your destination for first content, updates, and gaming.
Welcome to the fun.
First Updates Now is supported by the Milwaukee School of Engineering. MSOE offers week-long summer camps where high school students get to preview college by living on campus, exploring engineering programs, experimenting in labs, meeting with professors, and participating in fun group activities. Are you ready to experience STEM at MSOE? Visit msoe.edu/summer to learn more and register. First Updates Now is supported by Stryker Careers. Stryker's commitment to medical device technology innovation has made it a top career destination for those in First. First alumni and mentors are given top priority in their internship and career applications. Come create the next medical innovation that saves lives at careers.stryker.com.
So Zach, we're going to start with the cargo journey on your robot. Talk to me about, of course, not just what you have, but like what made you decide to go into the type of intake, the type of sorter, that sort of thing too.
Yeah, of course. So we went into the season not knowing exactly how we wanted to do our intake. We went with a few different versions of the intake, having a few with just one solid plate that would deploy in and out. But we eventually settled on a uneven 4-bar setup, just so that it could tuck nearly vertical and then extend out to the position that we wanted. Learning a few lessons from our 2020 robot, we wanted to make sure that this one was as robust as possible. So we went for as simple of a design as we could with it, yet still something that would be really robust. We have thick polycarb that just hard stops on itself.
Sure.
Yeah, so we essentially have a 3-roller setup here, 2 belts powering the front 2 rollers. And most of the optimizations that we ended up making with this intake over the course of the season had to do with jamming issues that we had near the sides. So we added on these little winglets near the end of the season, which, as you can see, they can tuck into our frame perimeter at the beginning of the match, and then they deploy out so that they can basically deflect the cargo into the intake when we're intaking from the side, or if it's near the edge of the intake.
Do those tuck back in every time when you bring it in, or is it just during the beginning of the match?
No, it's just during the beginning of the match,
Sure.
and then they're just loosely VHB'd on, so that once we deploy that first time, they'll snap out.
Makes sense.
And yeah, we also added these belts here. Both belts on either side help pull that cargo in as well. Yeah, we also, overall, on the robot, decided in about week 2 to fully remove all the air components from the robot. So we took our compressor off, and from that point on, we deployed our intake using a motor gearbox setup, which you can see right over here. Basically, we just have a gearbox that is powering a shaft that extends across the whole width of our robot, and then powers a sprocket at the base of both of these front arms. So that allows us to have an equal distribution of force on each intake arm.
Sure.
Yeah, that's been working pretty well for us.
Let's keep following your robot and keep going through the cargo. Of course, your cargo sorter has absolutely been phenomenal, so love to hear more about that, and let's go into your shooter too.
Yeah, of course. So we have this 3-roller setup for our ejector. These first 2 rollers, we were prototyping during probably about week 4. We initially started out with the concept of a flap that would open up in the back of the robot.
Sure.
Except the pneumatic actuation on it wasn't responsive enough for us. So we eventually went to this setup, and we found that these star wheels were really helpful due to how compliant they were. But essentially, we have these first 2 rollers that are belted to each other and powered here at the bottom of the robot. And then we have one back roller, which is independently powered by another motor And this makes it so that these two will drive the cargo in, and then depending on what color it is, whether we want to eject it or accept it, we will either send it out the back or up to our shooter using that independently belted one. And then it goes up to our kicker wheel and up to our shooter. Yeah, I mean, essentially with our shooter, actually another really cool thing that we were doing with our robot overall this year was we wanted to go into the season keeping our center of gravity as low as possible.
Okay.
So this means that, as you can see, all of the motors on the robot are basically below like this height. These motors on the climber and that one on the intake are essentially the highest ones that we have on the whole robot. Everything else is powered down to this powertrain that we see down here, including our shooter flywheel, which we have a long belt basically extending all the way down. And then it goes up, powers our flywheel, which then powers our upper rollers. Yeah, we prototyped with this, and we were able to actually come up with a pretty solid shooter design pretty early on. We were trying to decide between catapult or wheeled shooter.
Okay. So you're actually considering going with a catapult this year potentially?
Yeah, yeah.
Right.
We definitely we were worried at the beginning of the season about the effect that the fuzz could have on the shot consistency.
Sure. Yeah.
And so we went into prototyping and we saw that a wheeled shooter was still pretty accurate. And so we went with that, added some top rollers to it, and then put it on an adjustable hood. This is inspired by the 2910 hood from 2020 and then also from this year.
Sure.
Where basically there's just a 3D printed gear, and that acts as the back of our hood as well as what drives it up and down. And that is just powered, again, down at the bottom of our robot.
Let's go into software a little bit, hand it over to Porv, and talk a little bit more about what's gone into it. Especially love to hear about just how you're doing the color sorting, how you figure out the strategy even behind like what you want to do for that, and then of course anything from your shooter as well to the cover.
Yeah, absolutely. I mean, I think one of my favorite parts about this season has been that 1678 always designs really complex robots and we're trying to catch up with ourselves. But this year, because we went with a simple and robust design, we were able to add a lot more complex software
Sure.
to a simpler system. And that starts with, of course, the intake. We had no pneumatics on the robot since week 2. That means that our logic for the intake becomes a lot more simple in terms of having a simple deploy voltage and then holding voltage on each of the ends. And then that's tied with the singulator. So the moment our intake runs, our singulator runs. The reason I explained that is because this intake singulator system can act like a gateway for when a cargo enters our robot. And that's essentially the introduction to a slot-based indexing system. You'll notice we have a number of sensors throughout the entire cargo path in our robot. That starts with the color sensor right here. The rev color sensor also has this forward beam brake. We have a back beam brake, and then we have a top beam brake. Those sensors together map out essentially the entire path of the ball throughout the robot so we can keep track of where a cargo is at any point in time. This is really important for a couple reasons. One, we use this color sensor right when, again, this cargo passes through the gateway, right? We've passed through the singulators. We know that there's only one cargo going to be here. And we are able to decide whether that's a blue ball or a red ball. We actually did a lot of testing with our color sensor this year because I guess there's a lot of variability you can find in the sensor itself.
Yep.
A lot of teams have had a lot of experimentation to do with it because the proximity sensor updates at a different rate. There can be fuzz that attaches to the sensor.
Sure.
That messes it up. So what we do is we run a ratio of red to blue value on the color sensor, and then we essentially read whether that value is over a threshold. We don't use the proximity sensor within the color sensor at all because that updates at 100 ms, and we only want to be running at 20 ms, which the color sensor runs at. So when we read that our color ratio is above a threshold, we say that we have a ball. And if we have a ball, this entire indexing system starts to run. Now, at the moment we say we have a ball, we also decide what color ball it is. if it's the wrong color ball, then as Zach explained earlier, because we have a really simple system with deciding whether you want to index or eject a ball, all we do is we tell this ejector right here to run back or run forward. So we can eject a ball by running this through, and it comes out here, or we run this up and it goes to the top position.
When you guys are in autonomous and you have all the different designs for that, like what makes you determine like if you do like a really hard ejection, kind of where it goes back into their hanger or your hanger, that sort of thing?
That's a great question. Actually, we spent a lot of time figuring out the amount of compression we want right at this spot, because compared to a lot of other teams that also came up with the ejector tech, we do a lot of violent ejection. Especially in teleop, we eject pretty much at 12 volts on this motor in teleop. In autonomous, we do slower ejects because what we're trying to do is place the opposite alliance's cargo into our hanger. We have two specific modes for this. We have what we call a 2x2, which is where we pick up our own 2 cargo. Well, we have a preload, we pick up our other, we shoot that, and then we eject the opposite alliance's 2 cargo into our hanger. And then we have a 2x1 mode where we only pick the one on the far side.
Yeah.
The reason that those are slower is because we don't want the cargo to bounce off the alliance wall and then come back closer to the other team.
Gotcha.
So when you run it slower, it just neatly, gently places itself right in that hanger zone, and it gets a lot harder for another alliance to pick it up from there.
Is there anything, as we go and we go into your climber, is there anything from your shooter that you want to talk about in regards to this, like trying to figure out where, because you shoot from all over the field, obviously, right? Yeah. So like for you, is there like a certain sweet spot that Citrus prefers in general, and anything else you want to mention from a software side?
Yeah, I think the sweet spot is definitely any place from the hanger area, that safe zone. From there up into the fender, actually we have a separate shot for our fender because we know it's consistent and works every time. We can be ran by defense and it'll still work great. I think the cool piece of software about our shooter, there's 2 things. One, you'll notice we don't actually have any sensor for our hood except the integrated sensor within the Falcon.
Okay.
And that's because we decided to move away from Hall effects. In past years, we've used a hood or we've used a Hall effect for an elevator or something like that. And that sensor can be unreliable sometimes because, if it ever disconnects or anything, that's a failure point that can, I guess, break your entire teleop routine. So what we do instead is that we do something called current calibration, where we run the hood down at a really low voltage, and then we localize its position the moment it reaches a current spike. In regards to the shooting, because we have our limelight here, we run localization and goal tracking to know what our distance from the target is at any point in time. And because we do that, we're able to dynamically change the RPM of our shooter as it stays spun up throughout the entire match.
Sure.
And our operator, Helena, can shoot the moment we stop and want to because it's spun up to the right speed already.
Let's go over to your climber, and Helena, talk to me more about the mechanics of it and going into it. And I know you've had a few different kind of concepts for your climber through the season, watching some of the previous videos as well too. So I'd love to just hear what led into this climber.
Yeah, for sure. So we started with a climber that's pretty similar to a lot of ones that you'll see here, which first grabs onto the mid bar, then 2 bars, go back. And we decided that we didn't think we could get that to the speed and consistency that we wanted to get that.
Sure.
Then we moved into trying a similar climb to 125's climb, if you've seen it, that uses the high bar to grab onto the traversal bar. We couldn't get the geometry for that to work, as well as we were compromising a lot of parts of the rest of our robot to get that integrated into our robot. So basically we scrapped that, threw the whole thing in the trash,
All right.
and started with this one. So the coolest part about this climb is that the only non-passive part of the climb is the telescope. So we're using these WCP telescope blocks, as well as one that's in the bottom of this tube, which are driven by these Falcons and string. So you can see the gears here, and then the string is wrapped around that pulley that goes up through these and is tied at the top to the top of our hooks. So then with regards to the angle, you can see that we have these gas shocks here, which are pushing, and the motion is limited by these hard stop shafts, which are in these slots. So when we first drive this arm up, so our climb sequence is that we drive this arm up and then we pull down, and because our center of gravity of the robot is behind where the climber arm is, when we begin to pull off the ground, the whole robot leans back with the gas shock being compressed until the hard stop shaft hits the end of the slot, which gets us at the right angle to grab onto the next bar. So we extend this other arm up, grab onto that, and repeat that process, except on the last step, we integrate with the back of this hook instead of the front of these.
So as we wrap up, anything else from software, talk about that, and if we can show the climber deploy too, maybe take a look at that as well would be great.
Yeah, I think the climber software came down to a lot of robustness. There were a couple of failure points we saw. One was that the gyro itself, our pigeon IMU, receives drift throughout a match, especially when we're getting knocked around. So what we do is we actually wrote a wrapper for the gyro that allows us to measure an offset from when we start climbing instead of the original value on the pigeon itself.
Sure.
That means that we always receive the same contact angle, and thankfully we haven't actually missed a climb because of it yet, knock on wood. We run, we actually, I would say like there's a couple of safety checks that also go into this. We run current spike logic. We check that the strings don't have wear through software because of, I guess, like checking that we reach our hard stops with the position, etc. So that's the software regarding to that.
Do it. Show the climber just kind of go. I know we can't tilt the robot back exactly like that, but it'll still be cool to show off. This is a little bit how that sequence works on there.
Absolutely. I'll enable the robot right now if we can clear. Enabling. All right, so Zach, if you want to hold this for a moment. If we enter climb mode right here, the first step is always we extend our right arm. When we're facing the bar, this is the right arm to us. And then after that, the next step is that you pull down on one arm and you extend to a partial height on the next to make sure we actually clear the bar. Once that happens, you extend the next arm to its full height, and then you wait for it to hit the bar. And the moment it does, you pull down again and you extend the next one to a partial height. Then you do the same clearance sequence. You go up, and this time you lock on to that hook on the other side. And then this pulls down very gently to a partial distance.
Sure.
So we have a non-violent swing.
Well, 1678, really appreciate you taking the time. Tell us more about your incredible machine here. Looking, of course, to be division favorite, so can't wait to see your performance here. Let's talk about, division wins. It's 7 in a row now, something like that. Yeah, so looking for another one here. Good luck at this competition. Thanks a lot.
Thank you so much. Really appreciate it.
First Updates Now is supported by the Milwaukee School of Engineering. MSOE offers week-long summer camps where high school students get to preview college by living on campus, exploring engineering programs, experimenting in labs, meeting with professors, and participating in fun group activities. Are you ready to experience STEM at MSOE? Visit msoe.edu/summer to learn more and register. Thanks to Stryker Careers for their support in this video. First, alumni and mentors are making Stryker a top priority for their internships and careers. That's because Stryker knows that those in first are the leaders and innovators of tomorrow. If you want to help make the world a better place by creating life-saving medical devices and technology, get started at careers.stryker.com. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow, and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.